As I discussed in previous video, generator is a very powerful way to handle large streams of data, and we could achieve that data processing pipelines via generators. So what is a generator pipeline? Let's look at an example. Let's say I have a list of items and we have a function which processes on that list. This function gives me back another list of items which we can pass to our next function f2, which gives me another list of items which I can pass to another function f3. And this cascade of functions working on a list of items is kind of called pipelines. And we'll look at how we can create generator pipelines. So let's first look at a simple generator just to jog our memory. So here what we can see is I'm creating a generator of even numbers x for x in range of n if x mod 2 equal to 0. And because of these round brackets, this is a generator. And I can use the next function on the generator to get my even numbers. Let's run it and see. See, it works. But we could also have more involved generator. This is doing exactly the same thing. But the difference is that we are creating generator via a function. Define the even numbers, number is initialized to 0, we run a loop infinitely. Then there is this yield keyword which returns the number, but whenever we call next again, it kind of resumes from there. So it kind of remembers the state of the function where it left. So this should do exactly the same thing. Let's see. See, it gives us exactly the same answer, which is the first 5 even numbers. Now let's look at generator pipelines. Let me clear it up. So to start, I have defined here 3 functions. One is double, which doubles the input. One is power, which returns x to the power n. And one is add, which adds the 2 arguments x plus y. So let's look at an example of generator pipeline in the most basic form. So what we really want to do is perform a sequence of operations on each element of the list. So let's look at this function get pipeline. It takes an input, which is items, and this is, let's say, a list of numbers. Then we create a generator, which will take every item in the list and square it, because the power is 2, which leads to the generator called step 1. Now we can feed this generator into the next generator, and we can double the value of each element. This gives us the next generator step 2. Now we can consume this generator step 2 into the third one, where I add 20.333 to each element, which gives us step 3. This step 3 is used in the next generator, and we cube every element in the generator, which gives us step 4 generator, which is consumed by the next generator. And we are just rounding off every element to 2 decimal places, which gives us step 5 generator. And finally, we end with using the step 5 generator and add 70 to each of the elements in the step 5 generator. And this is the final state of our pipeline. And we return the generator. So this is our generator pipeline. Let's look at how we can use it. So using it is kind of very simple. We just create a list out of the generator with the input range 1 to 5, which is basically 1, 2, 3, and 4. Let's run this. So this is my answer, right? So we have seen how we can use a sequence of generator and each generator feeding into the next generator, right? So this is what is called generator pipeline. Although this is a very simple example where there's a one-to-one mapping between each stage of operation. So this could have been achieved by a different way as well. Let's look at that. So what we are doing here is the order of operation which we are doing in get pipeline, right? We could have just written a function so that the same order of operation is happening, which works on one number and returns one number, right? And then we can create a get pipeline like this. We take a list of items as input, we create a generator out of it, and we use the calculate method to operate on each item in the list. And this returns a generator. Now we can use that generator with an input range 1 to 5 and get our results and print our results. And because I have defined here get pipeline, we could actually comment this. Let's run this. So I'll not clear it so that we can compare. And it gives us exactly the same result. So now the question arises that if we could have done the same thing with such a simple code, why would we ever go back to our generator pipelines in this form, right? And there is an example later on where we are kind of doing data processing, where we feed in an array of numbers, it processes it in a way where the next stage is actually having a different number of items, right? We'll look at that, but the point is that the version which I have commented here is more powerful than the version which we are using in line 32. I'm just highlighting it. So that's one thing. One more thing we can do is do it in a way which is obvious. Let's clear all these up. So what we can do here, so just look at what we have done, right? Earlier we were defining our generator in a single line from line 13 to line 18. But each of these lines could also be done via a function. So step 1 is basically the generator for step 1 and so on. So this is exactly the same thing in the same order, and we could actually get a pipeline out of these generators. And if you look at line number 39, which I am highlighting, we could actually cascade all these functions and get the answer. And finally, we create a list out of that generator pipeline and show our results. Let's see this in action. Again, we run it and we can see the same results because we are doing the same operation just in a different way. So one thing to notice here is this, that line number 39 is something which I don't really like, in a sense that this kind of doesn't look that nice to me at least. So I'll just comment it. And what can we do alternate? What we can do is we can define a function pipeline. I'll just do that. So what have we done? So earlier, whatever we had done was already done. So everything remains common. It is just that how we create our pipeline. So in this example, what we are doing is we are creating a pipeline using reduce. So we first import some functools, a reduce function. Then we create a function called pipeline, which takes this tuple as input. Now, just look at what we are doing. We are using reduce function and lambda x comma y is equals to y of x. And we are keeping track of whatever we returned in x, and the new function which is in the steps goes to y. So basically we are recursively calling the function on the previous input. This is what reduce is doing. Not that hard to imagine that it is achieving the same thing what we are achieving in line 39 here. Now let's build a pipeline. So the pipeline is built and all the positional arguments are just all the steps in order. So first input is range 1 to 5, then step 1, step 2, step 3 up to pipeline end. The same operations, you get the results. So I'll just use this result, just call this get pipeline. Now let's see what we get. And we get exactly the same answer. So all this is good. What I am not liking about this current state of code is line 47, where we are actually adding the input as well, range 1 to 5. Wouldn't it have been nice if we could just have the order of the functions and we get a generator and we feed in the input to the generator again and again with various inputs, right? So let's do that. For that, what we can do is create a lambda function where input is items and we have a reduce function. And what was the third argument for reduce? The initial value. So it starts from this state, right? Which is this range 1 to 5 in this case. So now what we have achieved with this is that whatever we return is actually a function which takes an input, an iterable input, which is a list of items in this case. Let's run this. Let's remove this because that was the whole point of discussion. Now we can feed it into the pipeline here, right? So things looks good to me. I'll just run this again and we get the same answer. So what we have done till now is like a very simple example, but we have done the same thing again and again in various ways, and hopefully things have improved over iterations. But yeah, once we look at the last example, you will understand why generator pipelines is not the same as just using the function for each item. Now let's look at an example which is kind of a very trivial data processing pipeline. So let's do that. So what can we do? So in this example, what we are doing is we are showing a very basic data processing pipeline. So we have a generator read data which yields I from 0 to 4. For I in range 5, yield I. Then we have process data which takes in input. For item in data, yield item into 2. Def save data. For item in data, print saved item. Now we are just doing the same thing which we had done earlier, right? But if we just look at these functions independently, it kind of is very confusing in a sense that the first function is yielding me 0 to 4, and this feeds into the next function, which is also 0 to 4. And then it iterates through it and yields twice of each element. And then this list feeds into this. This is the right way to look at it, because if you look at it from a function point of view, then we kind of get confused that okay, what is data? What if data is only a number, not a list, and so on. But we should not think of it that way. We should think of it as generator pipelines. Let's run it and see what we get. See? So 0, 1, 2, 3, 4 was coming from read data. We doubled it, so it's 0, 2, 4, 6, and 8. And at the last stage, we are printing it, right? So this is one example of data processing. It's a very basic example, but that will help us understand all these things. Let's say I wanted to build a data pipeline with Python generators, right? So let's first look at an example what we want to do, and then later look at the code. So let's say I have a list of numbers. Let's call this input. Now what we want to do is just filter out the positive numbers. So these two will be removed. Let's call this operation filter where I is greater than 0. Or let's say x is greater than 0 is the criteria. Now what we want to do is kind of process the data in small batches. So we want to have like a fixed event window. So what will happen, let's say my window size is 2 and we want to process that in batches. So what will happen is the first number is in the first window, then second window. So window size here is 2, right? So I'm just trying to show what my result should look like. So let's call this fixed window or fixed event window of size 2. Once we have that, now what I want to do is for every window, I want to add it. So 1 plus 2 is 3, 3 plus 4 is 7, 5 plus 6 is 11, 15, 19, 23. So you can verify it that sum of every event window is here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We have 6 numbers, right? Let's call it fold sum. Now again I want to have a window size 3. So let's call it fixed window or fixed event window. Now what will we get? 3, 7, 11 and 15, 19, 23. Now what we want to do is get the median out of each window. So the median of this would be 7, the median of this would be 19. So let's do that. 19. So let's say I call it fold median, and then I just have a sink with the same name, which just forwards the values. So what are we seeing here, right? First thing is that we can see different stages where we are continuously processing data and feeding it to the next stage, right? And another thing to notice is that the number of items is going down in some sense, right? So what is really important here is that we are just trying to create sequence of generators to accomplish our task, and that is enough. Even for this complicated example, we are doing non-trivial data operations where even the number of items are changing because we forward the elements to the next stage in a certain way. So let's look at the code how we can get this. The first thing we are going to do is import a couple of things. Because we wanted median, we are importing median from statistics library. Then let me just paste a couple of functions and go through them. So let's go through them one by one. So first thing which we wanted to do was a filter operation. We wanted to have only positive values. So we have a function or a generator called filter numbers, which takes numbers, which is a list or a generator, and we are taking in a predicate. We go through each value in numbers, and if the predicate is true for that value, we yield that value, which kind of returns that value, right? Next was fixed event window, which again takes a generator or a list, numbers, and we take in the window size, and how are we forwarding the items, right? So we have an empty array, then we go through the numbers and we append into the array. If the length of array is greater than equal to window size, then we kind of make a copy of the array and we initialize the array to an empty array and we yield the result, which is the current window. So this kind of forwards an event window to the next stage. When we look at the real-time example, it will be very clear what I am saying when we say forwarding into the next stage. But for now, at least we can see that it is kind of creating a window of window size and yielding that. Then we are folding into the sum. So each window we are trying to find the sum and we are getting the next stage results. So fold sum is the generator here. So we go through all the elements and we are just yielding the sum of each window. The next one is once we have this sum, we again get the fixed window like this with window size of 3. We'll use the same method, fixed event window here. So there's nothing to discuss here. Then fold median and sync out. So fold median. So again we go through the array and each element here is a window and we get a median for each window and then yield that. Sync is nothing but it just prints the value and yields the value, which is like a forwarding kind of a stage. So these are all the necessary generators which is needed for data processing. Example we have just discussed. Now, what can we do? So this is very similar to our input. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The same input. Now we take that input and we use our generator filter numbers with a lambda function. Our predicate is just a lambda function which returns true when x is positive. Then after this stage, we feed in that filtered results into the next stage and window size is 2. So we are just creating fixed event windows. We get this generator which we feed into fold sum, which will create the sum for each window, and we get this generator which is fed into again fixed event window of size 3. So we get windows of size 3 with this generator, and again we have this fold median function which takes each window and finds the median of that window and creates a generator out of it. And the last one is sync, which is just forwarding and printing. We get this final results. Now, what we can do is we can just print the list of this. So let's run it. And what was the final result? 7 and 19. See, we get 7 and 19. It has printed 7 and 19 because whenever we have something in std out underscore sync, we are printing it as well. So this is all is interesting. Now I wanted to show you how this can also be used like for streaming data. So let's add one more function here. This is a slightly longer function, but let's do that because we need that. So there's this generator here which is std in underscore source. So first thing is we are taking inputs from the terminal continuously. So first thing we need is we want to try to convert to int if it's a value. So we try to convert. So we cast the value into integer and then return it. If we are not able to do that, we generate a value error and return none. Now what we will do is we'll keep on running this loop till stdin has something to send. Now if the input is exit, then we will break this loop and then we will try to convert the input into a value using the function we defined try to int. If the value is not none, then it prints the result and yields the value. So this is std in source, and let's add that so numbers here is now coming from the terminal std in. Everything looks good here. So what I want to do is actually I just want to print whatever we are yielding. So what I have done here is that I've added a print statement before the yield for every generator, right? So we'll be able to observe the results. So let's run this. So let's feed in the same sequence of inputs: -1, -2, 1, 2. So first thing we should see is that as soon as the generator gets the data or the generator sends the data, we are printing it, right? So as soon as we got two valid inputs, our first window was created, which was 1 and 2, and fold sum also received 1 and 2. Let's continue. 3, 4. Again, we fed in two inputs. So event window received 3 and 4, and fold sum received 3 and 4. Now we continue. We have 5 and 6. Now basically our fold median also received a fixed event window, because that's the first time it has been generated, because we need at least 6 inputs to get to this window. And once we have this event window, we find a median which is 7, and the sink has 7. Now we continue. 7, 8, 9, 10, 11, 12. Right? Now let's exit and see the results, which is 7 and 19. The same as what we wanted. So what have we learned here, right? First thing is we have used generator to kind of handle streaming data. So we are getting streams of input, and first thing is std source decides whether to accept the input or not, because it needs a number or at least something which is convertible to integer. So std source is handling the valid inputs in a sense. So that's our first generator. And filter number is our second generator, which kind of focuses on positive values, which std in source sent us. And then we have our filtered data. In filtered generator, we again create a fixed event window of size 2. Then we sum each window. Then we have fixed event window of size 3. Then we find a median. Then we get to the sink. And the interesting thing while we were running this streaming data thing is that as soon as we are getting data ready for the next stage, it forwards to the next stage. It doesn't wait for the stream to end, right? Because there's no end. So that's the super interesting part of this example. And with this, we have really seen how we can kind of create generator pipelines for data processing, or we could call this a data pipeline, right? So this was it about handling generator pipelines for streaming data. So we have seen data pipelines using Python generators. Let's look at a slight modification of it so that the code looks a bit nicer. So let's first define a class called pipeline operator. It just has a constructor which takes in a task and instantiates the instance variable task. Then we implement a reverse right shift operator which kind of runs the task on input X. So let's look at it, how we can use it. The first thing which we do is kind of create a pipeline operator for each of our functions. The first one is the filter number. So if we just look at it, filter number takes a predicate, which is lambda x, x greater than 0. And we just provide it beforehand and create a lambda function out of it, so that whatever function we have, it just takes one input, which is the generator for an iterable. Similarly, for fixed event window, we use a lambda function and pass 2 beforehand so that it knows what is the window length beforehand. Similarly, for window length 3, and so on. So we create a pipeline operator for each one of them. Now let's say I have a input list L. Let's have -1, -2 as well. Now we can create a generator pipeline burst by just using this right shift operator. So L right shift filter, then window for sum, then fold sum, then window for median, then fold median, and finally std out sink. Let's run this. So let's run the correct file, which is data pipeline generator.py. and see. So the final result is 17 and 9, 7 and 19, and this was the expected or desired results. So this is how we can use operator overloading to define a pipeline as well. So we just built our pipeline, our generator pipeline with right shift operator. But let's really understand what it is doing. For that, what we will do is read these two paragraphs. Let's do that together. The Python RR shift method implements the reverse bitwise right shift operation with reflected and swapped operands. So when you call x right shift y, Python attempts to call x dot r shift y first. And because that is not implemented, it will then see if Python has RR shift, which is a reverse right shift, where x and y are swapped, right? And if this is also not implemented, it raises a type error. The RR shift method is often used in practice to add right shift functionality to a class that doesn't yet provide it and cannot be modified as such as list or built-in data type. By implementing the method for other operand, you can still use right shift functionality for the class that doesn't implement R shift, right? And that's what has happened. So because L has not implemented right shift, so it will look at this and it will kind of reverse the operands. And in the way, what it is doing is filter numbers dot RR shift, and it passes along this list or a generator, and it continues to do so because generator also doesn't have right shift implemented. So every pair is kind of reversed in a way that this dot, okay, I'll just write it in a comment what is happening. In the first step, what is happening is we'll have filter dot RR shift L, let's call it maybe S1. Then my S2 is this dot RR shift S1 and so on. So you get the idea what is really happening with these two comments, right? And that's how pipelining is happening with this operator overloading using RR shift. So this is all about data pipelines using Python generators. I hope we have learned it nicely.